Picture this. We've just trained a massive artificial intelligence on the entire internet. Now, because it's literally read everything, it knows that roughly 50% of people believe a specific totally false misconception, right? But as an AI assistant, we want it to understand this misconception exists while absolutely never stating it as a fact. So how do we actually teach it the difference? How do we take a system that has memorized the messy, chaotic, and, let's be honest, often incorrect web and align it to be helpful, honest, and harmless? Well, it turns out the way we've been doing this is incredibly complicated, but what if we could just simplify the math?
Welcome to today's Explainer. We're diving into a genuinely groundbreaking paper from researchers at Stanford University titled Direct Preference Optimization. Your language model is secretly a reward model. This paper is a big deal because it fundamentally rewrites the playbook on how we control and align AI behavior. It essentially takes this notoriously unstable, computationally heavy process and turns it into an elegant, lightweight whiteboard lesson. If you want to understand how the next generation of AI models are being trained faster and way cheaper, you are absolutely in the right place.
Here is our roadmap for today. We're going to cover the AI alignment problem, the RLHF bottleneck, the DPO breakthrough, how DPO actually works, and finally, the results and real-world impact.
Let's kick things off with Section 1, the AI alignment problem.
So, when we build large language models, they start out entirely unsupervised. They soak up this broad world knowledge, but they completely lack precise control. So the very first thing we do is something called supervised fine-tuning, or SFT for short. This is where we show the model really high-quality examples of how to act, like how to answer a question politely, or how to write clean code. But here's the thing, SFT just isn't enough on its own. It's kind of like teaching a child a massive vocabulary, but failing to teach them any judgment. To get that precise steerability, to make sure the AI biases toward high-quality responses rather than just regurgitating average internet chatter, we have to teach it human preferences. Which brings us to Section 2, the RLHF bottleneck. For the last few years, the entire tech industry has relied on a very specific method to solve this preference problem, RLHF, or reinforcement learning from human feedback. But it has become a major roadblock. Just think about the sheer complexity of this pipeline. It has so many moving parts. First, you have to collect human preference data by showing human graders 2 AI answers and asking, hey, which one of these is better? Then you take that data and you train a completely separate neural network, called a reward model, just to act as a judge. And finally, you use complex reinforcement learning to train your main language model to maximize the score given by that judge, all while somehow forcing it not to drift too far from its original training. It's a lot. Honestly, RLHF acts like a multi-step Rube Goldberg machine. It requires that totally separate reward model. It uses proximal policy optimization, or PPO, which is notoriously sensitive and unstable. Plus, it requires you to constantly generate new samples from the language model during training, which just eats up massive amounts of compute. The ultimate goal for the Stanford researchers was to replace this fragile, heavy pipeline with something that's lightweight, stable, and driven by a simple classification loss.
And that leads us right into Section 3, the DPO breakthrough.
This is where the researchers asked a pretty radical question. What if we can bypass the complexity of RLHF completely? The core mathematical revelation of this entire paper is that your language model is secretly a reward model. The researchers actually proved mathematically that the complex reinforcement learning objective used in RLHF can be optimized exactly with a simple binary cross-entropy loss. Through a really clever change of variables, they realized you don't need to train a separate reward model at all. The language model itself can implicitly act as its own reward model. Let me give you a quick analogy to make this click before we get into the math. Imagine you want to train a writer. The old RLHF method is basically like hiring a separate, highly paid critic. You spend all this time teaching the critic what good writing is, and then the critic stands over the writer's shoulder, grading their work in real time while they write. DPO, direct preference optimization, says, you know what? Let's just fire the critic. Instead, let's take our writer, show them a good paragraph and a bad paragraph, and directly optimize their brain to prefer the good one. It's direct, it's efficient, and it completely cuts out the middlemen.
So, let's look at Section 4, how DPO actually works under the hood.
The methodology breaks down into 3 beautifully simple steps. Step 1 is the input. You just take a static, offline data set of human preferences, basically pairs of prompts with one preferred answer and one rejected answer. Step 2 is the process. You pass these through the language model using a simple classification loss, comparing the probabilities the model assigns to the good answer versus the bad answer. And step 3 is the output. You get your optimized final policy. There's no generating new text during training, no separate reward model network, just a clean, straight line to the goal.
The really crucial part is what's happening during that process step. When we look at the gradient update, the actual math that's modifying the AI's brain, it's doing something incredibly intuitive. It increases the likelihood of the preferred answers, and it decreases the likelihood of the dispreferred answers. But here is the absolute genius part. It dynamically weights these updates based on how wrong the model's implicit reward currently is. So if the model's currently assigning a higher probability to the bad answer, the DPO update hits it with a much heavier weight to correct that mistake. This dynamic weighting is exactly what prevents the model from degenerating.
Okay, beautiful math is great for a whiteboard, but does it actually work in practice? Let's transition to Section 5, Results and Real-World Impact.
The researchers tested DPO against traditional RLHF methods across 3 increasingly difficult open-ended text generation tasks. First up, a controlled sentiment generation task using IMDb movie reviews where the AI had to generate positive sentiments. Second, a TLDR summarization task using Reddit forum posts. And third, a highly complex single-turn dialogue task using the Anthropic helpful and harmless dataset, where the AI really has to act as an engaging, helpful assistant.
When we look at the sentiment generation test, the goal is to have high quality, a high expected reward, without deviating too much from the original training data. And the data shows DPO strictly dominating the traditional PPO method. It achieves the highest possible reward while maintaining a really low divergence. It's simply a much more efficient optimizer.
Let's move to a harder task, Reddit summarization. Here we're comparing win rates against human-written reference summaries judged by GPT-4 across different sampling temperatures. With the older PPO method, performance absolutely crashes as the temperature increases. It's just highly sensitive and unstable. DPO, on the other hand, it is remarkably robust. It consistently outperforms PPO, maintaining a high win rate even as you mess around with the sampling parameters.
Consider this key metric for a second, 61%. DPO achieves a peak win rate of 61% against the reference summaries at a temperature of 0.0. To put that into perspective, PPO's absolute best-case optimal performance was only 57%. DPO didn't just match the heavily tuned reinforcement learning standard, it easily exceeded it, virtually straight out of the box with minimal tweaking.
And the dialogue data brilliantly illustrates how well DPO scales to complex tasks. It was literally the only computationally efficient method that actually improved over the chosen human responses in the dataset. To get comparable performance to DPO using other methods, you had to use a baseline called best of 128, which, as it sounds, requires generating 128 different answers and picking the best one. That is massively expensive. DPO matches that heavy, compute-intensive baseline directly through its optimized policy, and it converges to this high performance incredibly fast during training. Now, to be completely objective here, we have to look fairly at both sides. The strengths of DPO are undeniable. It's stable, it's computationally lightweight, and it completely eliminates the absolute nightmare of RLHF hyperparameter tuning and in-the-loop sampling. However, the researchers do note some limitations. How well DPO generalizes to entirely new, out-of-distribution prompts definitely needs more comprehensive study compared to explicit reward models. There's also still a slight risk of reward over-optimization, where the model essentially learns to game the preference system.
So, what's the bottom line? What should you take away from this explainer? Well, for years, the AI industry has been bottlenecked by RLHF, relying on multi-step pipelines and fragile reinforcement learning to align our models. DPO proved that your language model is already a reward model. By using a clever mathematical trick, DPO simplifies alignment into a single, straightforward training step. It matches or flat-out beats traditional methods on real-world tasks, resulting in massive compute savings and significantly easier training for the entire AI industry.
Which leaves us with a pretty fascinating thought to end on. For years, compute and complexity were the limiting factors in making AI systems perfectly tailored to our human values. With scalable AI alignment now mathematically simplified by DPO, what unprecedented new capabilities are we going to unlock when these models can safely and efficiently learn our exact preferences? Thank you so much for joining me for today's explainer, and I encourage you to keep exploring the incredible, fast-moving frontier of machine learning.